The simple and best example to understand the Werner's theory is this one, COCl3 6NH3. Here CO plus 3 is called as central metal ion, and it is bounded by what means 3 chloride ions which are satisfying the primary valencies. So we can write at anywhere the Cl minus ions we can write anywhere. It is not necessary you write here or there, we can write anywhere. So this is called as primary valency, which is ionizable, the 3 chloride ions. The next one is 6 ammonia molecules. These are satisfying the secondary valency, which is having a particular arrangement which is known as octahedral arrangement. This is the octahedral arrangement. That means around CO plus 3, all 6 NH3s are arranged in the octahedral manner, and these are non-ionizable, and therefore these are indicated by what means a thick line. These are indicated by thick line. Now if you ionize this complex, then what happens means it is giving COCl, this one 6 NH3s as one component and present as one unit, and 3 chloride ions which are satisfying all this one CO plus 3 charge, they are ionizable, and that is why we are writing this complex as what means 1:3 type electrolyte. Next, the ammonia, whatever it is added for COCl3 is less in nature, then what happens means this is giving another one where naturally the 3 chloride ions are satisfying the primary valencies, because cobalt is having a charge of plus 3, and here since ammonia is less in amount, then 5 secondary valencies are satisfied by 5 ammonias, and the 6th secondary valency is satisfied by 1 chloride ion. That means among these 3 chloride ions, the 2 chloride ions are simply bounded by ionic one, whereas the 3rd chloride ion is satisfying both primary valency as well as secondary valency. As per Werner, the secondary valencies are non-ionizable. So therefore, what happens means it gives a complex CONH3 taken 5 times Cl, which is present as one unit having a charge 2 plus, and it is giving 2 Cl minus ions, and it is a example for 1:2 electrolyte. Again here CO plus 3 is there, all the 3 chloride ions are satisfying the primary valency undoubtedly, but we are having 5 ammonia molecules which are satisfying these secondary valencies, and the 6th secondary valency of cobalt plus 3 is satisfied by the chloride ion. That means one of the chloride ion is satisfying both primary valency as well as secondary valency. So therefore, during ionization, one of the chloride ion is not ionized and only 2 chloride ions are ionized. So therefore, this one is corresponds to 1:2 electrolyte. So therefore, it is treated with AgNO3 solution, means it is giving 3 moles of AgCl, whereas this one is treated with AgNO3, this one it is giving only 2 moles of AgCl precipitate. So therefore, they are what means giving different amounts of AgCl precipitates. Next one is the number of ions which are formed are also different. As I said, this is 1:3 type of electrolyte, and this one is 1:2 type of electrolyte. Total number of ions formed are 4 moles here per mole, 1 mole of complex, whereas here 3 moles of ions per 1 mole of complex here. So naturally here the electrical conductivity will be more and here the electrical conductivity will be less. So therefore they are differing in their conductivity measurements also, what actually Werner found, and from this one only he could able to explain the formation of these complexes by selecting the primary valencies and secondary valencies in criteria. And that means normal compounds are there, the metals, then they are showing what means one type of valency only in normal binary compounds, that is called as primary valency, which is there due to loss of valence electrons. Whereas in the formation of these coordinate complexes, what is happening means, along with showing primary valency, the metals are also showing secondary valencies, and that is due to utilization of their vacant d orbitals or vacant orbitals. Thereby what happens means, they are forming this type of secondary valencies and they are present as a new type of compounds called as coordinate compounds. This is the way of explaining the formation of coordinate compounds by Werner. The limitations of Werner's theory. First one, he successfully explained the formation of complex compounds undoubtedly, but what it is there means, he failed to explain the stability of the complexes. Stability of the complexes. Which complex is more stable and why it is more stable, and another type, some other complexes, why they are unstable. This type of one, the stability, he failed to explain. Next one is, second one is, he failed to explain the geometry of the complexes. Why geometry? Geometry of the complexes, they are differing. Some complexes, they are square planar. Some complexes, they are what means the tetrahedral shape. Some complexes are octahedral shape. Why these complexes? They are different in their geometries. So he failed to explain the geometries. Next one is, if we are selecting these ones, the complexes, some complexes are showing color. Why this color is exhibiting? And moreover, the same type of metal ion is present in the complex, even though the color which is produced by different type of secondary valencies are different. That what we are having in the first example, CO NH3 taken 4 times with Cl2, this one with 1 plus, it is green in color, one type of one is green in color, whereas same type COCl2 NH3 taken 4 times, this one 1 plus, it is violet in color. That means here the central metal ion is cobalt only, the secondary valencies are these ones. This is surrounded by 2 chlorides and 4 ammonias, 2 chlorides and 4 ammonias, but their colors are different. Why these colors are different? That is not explained by this one. And along with this one, magnetic behavior of these complexes are also not explained by this theory. So there are so many limitations for Werner's theory. He could able to explain successfully the formation of complex compound undoubtedly, but he failed in these aspects where he could not able to explain stability of the complexes, such as say metal carbonyls are very stable. Why they are very stable, metal carbonyls? There is no answer. Like that, geometry, why some complexes they are having square planar structure and some complexes why they are tetrahedral in nature. Color, as I said, some complexes are green color, and with the same type of formula, the same type of complexity showing violet color. color is not explained by this one. Like that, the complexes which are showing magnetic properties, what is the one which is responsible for this magnetic property is also not explained by this theory. So, these are the limitations of Werner's theory. In the complex compounds or coordination compounds, these are the terms what we come across. One is coordination entity. What is meant by coordination entity? The coordination entity is the one where the metal atom or ion is surrounded by the certain number of atoms or groups or what means the ions, which behaves as a single entity. That means, say for example, in what means CONH3 taken 6 times, this one it is there, the CO is bounded by 6 NH3s and that is behaving as a single unit, and such one is called as coordination entity. The second one is central atom or ion. Here in the formation of this complex, the metal atom or ion, in this example CO plus 3 is the one, CO plus 3 is called as central atom or ion which is bounded by the species and it is present or bounded by the secondary valencies and behaves as single unit, that is called as central atom or ion. Next one is ligands. What are the substances or the species which are there, which are forming the secondary valencies or satisfying the secondary valencies? They may be simple ions, or they may be molecules which are actually giving rise this coordination entity are called as ligands. These ligands are so many types, we will discuss again this point later. And next one is coordination number. If you select this coordination number, the number of dative bonds formed by this central metal atom or ion during the formation of this coordination entity is called as coordination number. Generally, this coordination number is fixed for certain metal ions, such as say for example Zn plus 2 is there, coordination number is 4, like that Cu plus 2 is there, coordination number is 4, say for example Fe plus 2 is there, ferrous ion or ferric ion, or these ones are there, generally the coordination number is 6. That means they are surrounded by 4 or 6 ligands and they can form 6 dative bonds like that. So, therefore, such one is called as coordination number. Next one is coordination sphere. Whenever the central metal atom or ion is surrounded by ligands and these ligands are satisfying the secondary valencies, they behave as a single entity, and this single entity is indicated in square bracket, and this one is called as coordination sphere. This one is known as coordination sphere. That means here CONH3 taken 6 times, 3 plus is a coordination sphere, and the one it is say for example FeCN taken 6 times, 4 plus is coordination sphere, and this charge is balanced by the oppositively charged ions. Here the balance of charge is there by 3 chloride ions, and here the charge 4 minus is balanced by 4 potassiums, 4K plus ions here. So, this one is called as coordination sphere. Next, coordination polyhedron. This coordination polyhedron indicates what means the spatial arrangement of these ligands around this metal atom or ion in the formation of complexes. As we discussed previously, these complexes will have what type of one means the geometry as tetrahedral geometry and square planar geometry, octahedral geometry, and you are describing what is the geometry of this coordination sphere, that is called as coordination polyhedron. Next one is oxidation number of central atom. Whenever we are selecting, whenever we are removing these ligands with their electron pairs along with them, then what is the charge present on this central metal atom is called as its oxidation state, which is indicated by Roman letters in parenthesis. That means here the cobalt is having 3 units of positive charge, that one is indicated by 3 in parenthesis, that means in brackets, that is called as oxidation number. Next, homoleptic and heteroleptic complexes. What are homoleptic? The one, suppose say for example the cobalt complex here, this one is having NH3 as ligands, all these ligands are similar type, and this type of one is called as homoleptic complex. Whereas here in the second case, CO, Cl and NH3 taken 5 times 2 plus, then in this complex the ligands are what means actually corresponds to different ones, and such ones are called as what means the heteroleptic complexes. So therefore these are the terms what we come across during learning of these coordination complexes. As we discussing ligands, this is very important one. Ligand is the species, may be a single atom, or it may be a simple ion, or it may be a molecule which can donate an electron pair in the formation of these coordinate compounds to metal atom or ion through a dative bond, and such ones are called as ligands. That means if you select this Werner's theory, we learned that the metal atom or ion, it will be forming 2 types of valencies, that means 2 types of bonding nature it is exhibiting. One is primary valency and second one is secondary valency. These secondary valencies are covalent in nature. This covalent character is attributed there for this metal atom or ion due to formation of coordinate covalent bond, that means dative bond. In such a case, there must be a species which has to donate an electron pair for the formation of this dative bond to satisfy the secondary valency. Such species which is there to form a dative bond with the metal atom or ion in the formation of complex is called as a ligand. The ligand, there are different types. One is so called as unidentative ligand. What is meant by unidentative ligand? The ligand bound to the metal atom or ion through a single donor atom. That means it forms one dative bond, such as say for example Cl minus ion, or say NH3, or say what means PH3, or say what means R3P. These type of ones, they are able to donate a lone pair of electrons and they will form a one dative bond, and such ones they are called as unidentative. Here uni indicates bonding capacity is 1, and that is done by the ligand having single donor ones, and they are called as unidentative. These unidentative may be ions such as simple ions such as say Cl minus or OH minus, or simple molecules such as NH3 or PH3, like this. Second type of ones are didentative. Certain times in certain books we come across bidentative also. Here di or bi indicates that metal atom or ion with that one. These ones are bounded by 2 donor atoms. That means here they are forming 2 dative bonds, such as a very simple example which commonly we come across is ethylenediamine. This one is ethylenediamine, which contains 2 NH2 groups, where that is 2 nitrogen atoms working out as 2 donor atoms, and that is forming what means 2 these dative bonds, and such ones are called as didentative or bidentative. Another simplest example what we come across is COO minus oxalate ion. In this one also 2 oxygen atoms which are present here, they will form what means 2 dative bonds, and such ones are called as didentatives. And while forming these 2 dative bonds, they may be giving a cyclic type of compound also, which is called as chelation. That means the one whatever it is there, for example, say for example CO plus 3 is there. If ethylenediamine is present, this is ethylenediamine, then this one NH2 acts as a donor, and here this NH2 acts as a donor. So therefore, while donating these lone pairs for the central metal ion, it is forming a ring type of structure, and such one is called as chelation. And such ones which are forming this type of ring structure are known as chelating ligands. What they are called as? Chelating ligands, which is forming this type of ring type of structures. And another one, polydentative. Generally the ligands which are forming more than 2 dative bonds, they are called as polydentative ligands, such as what means EDTA, ethylenediamine tetraacetate, EDTA, and this type of ones they are called as what means polydentative ligands. These polydentative ligands may donate only 1 electron pair, and depending on the nature of the central metal atom or ion, they may donate more than that one. That means these polydentative ligands, they are what means acting as different manner. That means they can donate 1 dative bond, or they can form 1 dative bond, or they can form more dative bonds. So they can flexidentative also. Polydentative ligands or flexidentative ligands.